is Professor Luzia Trinca from trying to practice a little bit of Portuguese. Universidade Estadual Paulista.
Thank you very much. Well, this work is very much in collaboration with Stephen Gilmore, and I would like to thank all the organizers for this excellent opportunity, and also yes, shall I put here? But this red, the light is red.
The microphone projects very much, so you just try and speak very loud. Okay. Really, the microphone is just good.
Can we put it on a higher volume or something like that?
I don't think so. I think the microphone is mostly just for the recording. It does. There are some speakers at the back. It does project across the speakers.
So I will try to speak louder. So I would like to thank all the organizers for this excellent opportunity, and the EPSRC for funding my visit to the UK. Well, I have included two words in the title, response surface designs, because it's about that I will talk. Well, I will give a short introduction, introduce some notation, talk about some usual optimal criteria, and propose some new optimal criterion for our purpose, and give some illustrations and some comments. So, response surface, the objective is usually to study the relationship between a response variable and several quantitative factors. Usually this relationship is approximated by a low second order model. So for example, here, the second order model. The researcher may have several objectives, for example, estimate the optimal conditions, or to find important factors, or make more formal inferences about the effects of the treatments. And we will in this talk be concerned with this objective. So we know that if we focus in one objective, we get one different design. We will talk a bit about that. So the experimental units may be heterogeneous, so we may need blocking factors. There are several studies in the literature focusing in orthogonal blocking and optimal blocking for small block size. But in this talk, we will propose criteria that allow an unbiased estimate of sigma squared, the so-called pure error, among other properties, in order to make valid inferences about the treatment effect. So, at first, let's have a look at the definition of pure error. That is the unit by unit variation from genuine replication of treatments. The importance of estimating pure error has been mentioned in several textbooks when analyzing experiments, we consider that it is very important when we want to make inference about the parameters, and it is not being considered directly when we construct designs by algorithm approaches. So, for example, just a review for estimating pure error. Let's consider this unblocked design, 2 factors at 2 levels and 2 center points. We have 5 treatments, each one appearing twice. So for the treatment model, we have 4 degrees of freedom for treatment. 2 can be used for linear effects, 1 for interaction, 1 for curvature, and 5 degrees of freedom for pure error. That will then allow us to get an unbiased estimate for sigma squared. If the design is blocked, the obvious blocking, 2 blocks of size 5, we then get this decomposition of degrees of freedom. 1 degree of freedom from pure errors is used for blocking. So for blocking cases, we are considering that, as usual, there is no interaction between treatment and block effects, and so that's, we can say, is pure error. So in both cases, then, if the design is unblocked or if it is blocked, we get an unbiased estimate for sigma squared. So I will give some notation that I will be using for defining the criteria. For the unblocked designs, in matrix notation, the usual notation, the expected responses equal or approximated by a X matrix times beta. These numbers are the dimension of the matrix. I will write the model like that, and separate the intercept just to make notation easier. And so the information, the full information matrix is given by that, and the information matrix for the parameters that we are interested is given by this expression, and the variance of the estimators is proportional to the inverse of m beta. For the block design, we use the same idea. So in this part, I have the part of the model related to the factors, and here for the blocking factors. The information matrix can be written like that, and the information matrix for the beta parameters can be written in this way, and we get the expression for the variance of the beta hat. So I will use this B here to indicate that the design is blocked. So the usual criteria, I will mention only 2 of them that are the most popular. For the unblocked design, we minimize the determinant of the inverse of the information matrix, or maximize the determinant of the information matrix. and that is argued to be minimizing the volume of the confidence ellipsoid for beta. That is the D criterion. We have also the weighted A criterion that is more sensible for this type of models instead of pure A criterion that minimizes the weight mean variances of beta hat. So W here is a matrix, a diagonal matrix, possibly with unequal weights. So these criteria are okay if sigma is known. So they, in fact, have these properties. But, and also we can use these criteria if we are comparing designs with the same degrees of freedom for pure error. For blocking, I will be mentioning criteria for blocking a fixed treatment set, and so in case of D, we can say that the D efficiency is the ratio between the determinants of the inverse of the matrix, the information matrix from the unblocked design by the blocked design. For the A criterion, as well, we can define this efficiency. That is, so the mean, the weighted mean part of the variance for the unblocked design, and that's for the same for the blocked design. And also we can think on the efficiency factors for each parameter, and we have this M criterion, we call M criterion, that is the mean efficiency factor. Can also be weighted, depend on the interest. These are also fine if we know sigma squared and or if the designs we are comparing have the same degrees of freedom for pure error. So if we block, when we block, we don't lose any degrees of freedom. So that is the D efficiency or the A efficiency or whatever. But if sigma is unknown and we have to estimate it from the design, in the unblocked design, the 101 minus alpha percent confidence ellipsoid volume for beta is proportional to that, where F is the quantile of the F distribution for P minus 1 degrees of freedom in the numerator. P is the number of P minus 1 is the number of parameters in the beta vector, and D is the degrees of freedom for pure error. So, if we want to minimize this volume, we have to minimize all that and not just that. So, this will lead us to call a new criteria called DP criteria, where P means pure error, allowing for pure error. The same we can say if we think in constructing confidence intervals for individual parameters. So for parameter beta I, the confidence interval is proportional to that, And so, if we want the length minimum, we should minimize that expression. And that will lead to a AP criterion or weighted AP criterion. So, D is the degrees of freedom for pure error for the F distribution. For the unblocked design, we have the same ideas, and so the efficiency for the block design with respect to the unblocked design, you have this part to take account of pure error from the block design. So again, if the blocking don't use any degrees of freedom from pure error, that will be 1. And we have the same idea for A criterion. And for if we want the relative efficiency for individual confidence intervals for individual parameters. So, well, I forgot to define here. D is degrees of freedom for the unblocked design, and dB the degrees of freedom from the blocked design. So, for example, if we have 4 factors, 3 level factors with this treatment set, that means S4 means the part of 2 levels. Each factor has 2 levels, so 16 points here for 4 factors. S1 means 1 factor varied, have levels at +1 and -1, and the others are centered. And S0 means all factors are at the center level. So we have 25 treatments, and we have 36 combinations. 25 of them are distinct. Let's consider blocking this treatment in 9 blocks of 4 and having as a base the second order model. So in that case, P is 15, including the intercept. And so for the unblocked design for that treatment set, we have 25 degrees of freedom for treatment, 14 for the model, 10 for lack of fit, and 11 for pure error. If you use the D criteria to block this treatment set in 9 blocks of 4, we get this decomposition. We use 7 degrees of freedom for pure error for blocking, and 1 degrees of freedom from the lack of fit. So 1 treatment contrast is used for blocking. We use the DP version, that is taking into account the pure error degrees of freedom. We have things in the opposite direction. We have 7 degrees of freedom from lack of fit are used for blocking, and just 1 from pure error. So we end up with 10 degrees of freedom for pure error. And 3 for lack of fit. If we use the M criteria, I forgot to say here that for DP criterion we need to fix a confidence level, and the confidence level for the confidence ellipsoid, and here was fixed to 5%, the alpha. And so for the M criterion, the usual M criterion, we have 5 degrees of freedom from pure error for blocking, and 3 from lack of fit. And the version for pure error for the M criterion, we get something like 5 degrees of freedom from from pure error goes for blocking, and 3 from pure error. 3 from pure error goes for blocking, and the other 5 is from lack of fit. So we see here the DP criteria is much more extreme than the MP in terms of getting more degrees of freedom, and that is because for MP criterion we are not doing any correction for multiple comparisons. I use the same 5% alpha. So we looked at several cases, and we thought that these criteria, they are sometimes too extreme. So they focus on pure error, but maybe for some case they will be too extreme, and we won't have anything here for lack of fit. We can have. So that leads us to think about the efficiency of resource using, because we may end up with a design that there is no degrees of freedom if we want to fit any further order term. Well, there are some studies about lack of fit, focus on lack of fit, but usually they require some type of specification of potential terms in the model. But we could think about the use of resource, and there is this definition we borrow from Daniel in his book, the definition of degree of freedom efficiency, that is the ratio between the number of treatments and the number of units we have in the experiment. So if we maximize that, of course we go against our pure error criteria, that we would then minimize the pure error degrees of freedom. But we could use this idea and combine with our criteria to get a more perhaps equilibrated design. So for the blocking case, an extension for the degree of freedom efficiency would be comparing the number of treatments that are allowed in the blocking and no blocking. So we could then use all these criteria to write a very general criterion in the same fashion as proposed by Atkinson, Donovan, and Tobias. We have several properties that we can give weights for each one according with the objective of the experiment and design an appropriate experiment based on that. So these weights, they add to 1. So in our case, let's call A1 the DP efficiency, A2 the MP efficiency, the A3 M efficiency, and A4 the degrees of freedom efficiency. So, for example, if we want a good design for pure error, we set this and we are interested in global F-tests or joint confidence region. We use 1 here and 0 for all the others. If we want some X to be able to fit some extra terms, we can use a compromise between this and this. If we want to make individual tests or individual confidence intervals for the parameters, we could use that or a compromise with that. So we have several approaches here. So, well, I already mentioned that. So let's show the example. So I have here the example that I already showed for 9 blocks of 4, and here a compromise criterion between DP and degrees of freedom efficiency. So we have here a balance among the degrees of freedom. And the following is for MP compromise design. So focusing on MP and degrees of freedom. We notice here that the compromise M goes have even less degrees of freedom than the standard design. And here we should note that these two designs, they have the same degrees of decomposition, but they are not equivalent. They have different efficiencies. Just show another example. Just one thing to note is that the DP efficient design gave something like that. That is a block. All center points in one block. And, well, we might not like that. So it's good to think in a compromise criteria for not getting that. This is just another example for two-level factorial. In 6 blocks of 4, we have 16 treatments, distinct treatments, and 8 of them are with duplicate. So we have 15 degrees of freedom for treatment, 8 for pure error, and 5 for lack of fit on the on-block design. And we get something very similar to what I showed before. The standard criterion, they usually penalize pure error for blocking, and we can more or less get something more, perhaps more sensible, using a compromise criteria. So, to finish, I would like to say that the standard criteria assume that sigma squared is known. If that's not true, we should design that allow the estimation of a valid, allow a valid estimate of sigma squared. And this idea of compromise criteria is very simple to implement and in a very easy way. And we are working on this type of criteria for choosing treatment sets, and they have a much greater impact in that case. So, yes, I shall finish. And I thank you.
Questions or comments?
I'm just wondering how you're choosing the weights in your compromise criteria.
Well, we can try some weights and look at the designs. For example, for the compromise, I start with, for example, this is one suggestion for example, for the D compromise. Give half weights for DP and half to DF efficiency.
So you could do something where you are setting those weights across a range of values and then plotting your degrees of freedom for your pure error and lack of fit, and then choosing it.
Yes.
When you introduced your criteria, new criteria, you spoke about that you look for the volume of the confidence ellipse or for the length of the confidence interval. But in fact, in practice, this will depend on your estimate. So it's some kind of expected volume. Or
Yes. Yes. It's just in order to get a valid estimate of sigma squared.
Really, you are comparing across designs where the degrees of freedom for errors and blocks change. Does that mean the number of blocks may change from one design
No. The number of blocks are fixed. They
Yeah.
are fixed.
So I mean the criteria you had up just appear to be proportional. The standard criteria, the constants were percentage points of.
What is changing is the degrees of freedom.
Yeah, that was my question. Yeah.
What changed is that dB.
Degrees of freedom for blocks.
Degrees of freedom of pure from blocking.
I think that it's not. Sorry. So let's thank Luzia once more.